In this video, I'm going over how to calculate the activity level of a radionuclide after a given time using the half-life of the radionuclide, the initial activity, and the elapsed time. This is also referred to as a decay equation. I'll begin by explaining the concept of half-life, which is the amount of time required for a radionuclide's activity level to decay by 1/2 of its initial value. Graphically, this decay is a logarithmic function, with activity on the y-axis as the dependent variable, and time on the x-axis as the independent variable. Because it's a logarithmic function, it will decay over time to very, very, very close to zero, without ever reaching zero. A radionuclide with a shorter half-life will decay faster, and a radionuclide with a longer half-life will decay more slowly, just like this. The half-life itself is a property which is constant and innate for each individual radionuclide. Now for the equation. Activity at a given time is equal to your initial activity level times e to the negative lambda times time. Lambda represents our decay constant, which is a function of the half-life and equal to the natural log of 2 divided by the half-life of the radionuclide in question. If we plug the decay constant into our decay equation, we see that the activity at a given time is equal to the initial activity times e to the negative natural log of 2 times time divided by the half-life. An important thing to also recognize is that the activity levels are directly proportional to the mass and to the number of moles and to the percentage of the radionuclide present. So this equation can also be applied to those concepts as well. So let's look at a problem where we're given a radionuclide source with an initial activity level of 130 picobecquerel. After 1 month, or about 30 days, given a half-life of 8 days, how much radioactivity would we expect to remain? This particular radionuclide in question is iodine-131, which we would have to know has a half-life of 8 days. Again, the half-life is a property of the specific radionuclide, so this is something that we could look up and verify. We're looking for the activity after this given time has elapsed, and the activity at a given time is already on the left side of the equation, so no rearranging is necessary here. We're just going to plug in what we've been given and solve for the activity at a given time, which is sometimes written as A of F or activity final. Activity at a given time, we could even put 30 days in parentheses here, is equal to our initial activity of 130 picobecquerels times e to the negative natural log of 2 times 30 days, or 1 month. We're using 30 days here so that our units cancel out, divided by our half-life for iodine-131 of 8 days. It's important that the units cancel out because we can't raise anything to the power of e that has units attached, so this portion of the problem must be unitless. If we plug this into our calculator, we should get 9.7 picobecquerels of iodine-131 remaining after 30 days, with our initial activity level of 130 picobecquerels. We can do a quick logic check here too. With a half-life of 8 days, the initial value should have dropped by half more than 3 times, since 8 goes into 30 over 3 times, which would bring us from 130 picobecquerels to 65 after 1 half-life, or 8 days, to about 32 after 2 half-lives, which is 16 days, and then about 16 after 3 half-lives, or 24 days. So we expect that our value would be less than 16, which checks out. We also want to verify that this number is above 0, since the activity level over time approaches 0, but never reaches 0, and certainly is never a negative, so that's an important check on our math as well. Now this problem was in becquerels, which is an SI unit, but we could also convert this into curies, which is a more standard unit in the United States. This is a simple process where you're going to use what are commonly referred to as railroad tracks. We'll start off by placing our answer at the top, and we need to end up with curies at the top of our railroad tracks. To accomplish this, we need to know that there are 3.7 times 10 to the 10th decays per second, or DPS, in a curie, which we want on the top of our tracks. We also have to know that 1 decay per second is equal to 1 becquerel. We're putting the DPS diagonal from the other in order to ensure that we can cancel them out, because we want to end up with only curies at the top. Now we have becquerel and picobecquerel remaining, and we know that there are 10 to the 12th picobecquerel in 1 becquerel, because a picobecquerel is very small, so it takes a lot of them to equal 1 becquerel. We're putting the picobecquerel on the bottom so that it cancels out with our answer that was in picobecquerels. And this leaves us with becquerel at the top to cancel out with the becquerel that we had left on the bottom earlier. By the same concept, we can convert our remaining curies into picocuries. Plugging this into our calculator, we end up with about 2.62 times 10 to the minus 10th picocuries as our answer. Now with this information, you should be able to apply the decay equation to other radionuclides and time periods in order to determine final activity levels. This equation could also be rearranged to solve for elapsed time or even the half-life of a radionuclide if you're given an elapsed time and initial and final activity level. Thanks for watching.